All right, this is the third video on 6.2. So I'm going a little fast here because we have already done the eigenvalue and eigenvectors. It's all the problems are worked out here, but I'm just gonna go quicker, right? So find the general solution. Now we need to figure out the general solution of this first order differential equation. You have two equations here, okay? So we need to figure out what is the solution. So again, they gave you the problem like that. I can rewrite this problem into like this one too, if I want it. Like I don't have to do that, okay? First, look at this A matrix. A matrix, I'm gonna find out eigenvalues and corresponding eigenvectors, right? So remember that, go back and review your how to find the eigenvalues. So A minus lambda I, and then lambda is your eigenvalue, okay? So 2 minus this, right? This is 2, and then you're going to subtract alpha there, lambda there, and then you're going to find the determinant of that, right? Determinant of that, and then you're going to see your lambda is 3 and 5. Now remember that if you have a distinct real eigenvalues, then you're going to have your format, right? So you need to remember that format. Again, if lambda is your 3 is your eigenvalue, and then you're going to plug in here in this matrix. Right, so just plug in there, change into row echelon form, reduce row echelon form, and then you're going to find like you're going to set up like this, like find the kernel, right, x and y, and you're going to find that like a 1 and 1 is a vector for that lambda -3. So eigenvalue is 3, your eigenvector is 1, 1. Similarly, when eigenvalue is 5, you plug in there for 5 for lambda, right? If I plug in there, again, remember that this is the matrix A minus lambda I, go there, and just plug in there for 5, right? 5, 5. And you're going to see that matrix. Change into reduce row echelon form, okay? And then again, this is the kernel. You need to find the kernel. So that is the eigenvector. 1, 3 is eigenvector. And that's my solution now. Again, C1 is the constant, C1, C2s are constant. E to the power, this is eigenvalues, these are lambda, and that's also lambda. And this is my eigenvectors, and that's my solution of my differential equation, okay? But now if I want to draw the trajectory, right, trajectory, then what you can do is that eigenvectors, I'm going to draw that eigenvectors 1, 1 and 1, 3, look at here. I just draw the line because it goes through 0, 0 is equilibrium. So you draw the line through the 0, 0, okay, through 0, 0. And since your eigenvectors are positive, if the eigenvectors are positive, then their solution go away from the equilibrium, right? So that's called unstable. Remember that, that's we did a long time ago, right? So unstable, these are all stable at the equilibrium at the origin, okay? Next one, very similar. Again, we have this differential equation. I need to find the general solution. And then we're gonna sketch the eigenvector, okay? So here again, A lambda I, so find the eigenvalues. Again, this is the determinant of this matrix. I found that lambda equal to +2, -2. And when lambda is +2, you're going to find that matrix and then do the row echelon form. And again, do that kernel, find out this vector. So that's my eigenvector. Similarly, if lambda is -2, you can pause this one and look at it and do yourself, right? Again, I'm just going to plug in -2. -2 makes it positive. That's why I just put the positive there. So this is my vector, the matrix, right? And this is a singular matrix, right? So that matrix change into reduce row echelon form, and then this is always the case, right? This format is going to be always like that when you do the row echelon form, right? 0, 0 in the bottom, and then you get that eigenvector for that particular lambda, and then that's my solution. Right, here the solution is when t goes to infinity, what happened is this goes to 0, right? It converges. It's come closer to 0, right? It shrinks to the equilibrium, right? So that's why it's this this is stable, right? But since there's other eigenvalue is positive, it's when t goes to infinity, that's going to what happen is it's diverts from the equilibrium, right? So that's why it's semi-stable. One is stable, one is unstable, so that's why it's semi-stable. Equilibrium at 0, 0. Okay, so I'm going a little fast. I know you need to pause this one and watch it. Okay. All right, next one is if there's initial condition. The same problem, similar problem, just you need to add the initial condition. Again, I need to find the eigenvalues, eigenvectors. So I do that. I found the eigenvalues. You pause this one and make sure you get the right eigenvalues. And then after I get the eigenvalue, I get the eigenvectors for each eigenvalues, like a -1 and 4, there's a 2 eigenvalues, and then I have eigenvectors. You can write the solution in a general solution. This is my general solution, right? C1 e to the power eigenvalues in -1 here, and there's a 4 here, and eigenvectors are over here, right? Now, if I plug in t equal to 0, because that's the condition here, they give t equal to 0, and then you're going to have, this is my initial condition. So just plug in there. That's my initial condition. And then you can see that there's a 2 equations comes out like that. And you can solve for C1 and C2, right? And after your C1 is 0, so that means whole thing, this one disappears, right? And C2 is -1, so that's my solution for that initial value problem. All right, one more problem. I know I'm going a little fast here, but you definitely can stop and then do this one, okay? Again, my differential equation here, this is homogeneous. That's why the solution always go through 0, 0, right? That trajectory, the vector always go from 0, 0, the eigenvectors. So again, this is how you start with the eigenvalues. And then I found the eigenvalues are both negatives. All right, both negative means it's going to be stable because they're moving towards 0, 0, right? It's still homogeneous. That's why it's towards 0, 0. When it's a -1, I got my eigenvector is 1, 1. When is -4, my eigenvector is -2, 1. All right, so you check this one, you do your own. And then my solution, general solution, is again this one, C1, C2, e to the power -1 is -4, that's 2 eigenvalues, and then these are the corresponding eigenvectors. Okay, and then if I draw this one eigenvectors over here, so that's going to be 1, 1 is going to be like that, and then -2, 1, so -2, 1 is going to be here. And since both they are going from 0, 0, that's equilibrium, and they are both going towards 0, 0, right? Because they are both negatives. So that's why it's stable. Now, initial condition, again, when it's 0, you have a -1/6 that's given. And when I plug in t equal to 0, the e to the power negative t is going to be disappears. That's why it's 0. That's going to be 1. So that's going to disappear. And you have 2 equations. You solve it, and you're going to get C2, you got this. C1, you got 11/3. Just plug in there, and you get the solution. All right? I know I did so many problems very quickly here. You can look at this, and if you have any comment, let me know.